Okay, so your exam is tomorrow night. The review outline is posted. That should be like the centerpiece of your studying. So everything on the exam is talked about in that review outline. Okay, and then from there you're reviewing. So the most important things are what we emphasize in lecture. Okay, so your lecture, the lecture videos, the quizzes, of course, are all the most important things each week. What else? Homework. So there's lots of things that you have to use to study. Okay, but that review outline is the centerpiece, and that's really where you're marching down the list and saying, do I really understand this the way it's saying? If not, I need to go find homework problems, quiz problems, whatever, or get help to reinforce those things that you're not understanding. Let's see. In terms of tomorrow office hours, so Julia will have her normal office hours. But then Morgan is going to join her, and that's in the conference room in ECA 385. ECA, is that your normal spot for office hours? All right, so her normal spot for office hours Wednesday afternoon. Morgan will also be there, so extra help. So lots of you can come. And then after that, starting at 4, then Ben is going to come for a little bit even longer. So Ben is, no, not Ben. Eugene is going to come for a little bit longer. So pretty much 2:30 on throughout the afternoon, you've got support there on the ECA 3rd floor, 385, and then with Eugene.
Those office hours are at 2:30. Is that when you start? You said.
When do yours start, Julia?
2:30, but Erica's starts at 2:30 and 4 here at ECA 385, and then Eugene has a class. So as soon as he gets back from his class, he's going to take over and be in his office.
But is there office hours before that too?
Yeah, Erica's. Yeah.
Those. Yeah. So just look on the schedule. Erica will have her normal office hours from the other lecture. That will be before that. So it's pretty much all afternoon. You've got support there in 3rd floor ECA.
Like I have office hours in the morning from 8:30.
And then Morgan has more office hours in the morning. So it's office hours all day. Okay. All day according to the regular schedule. And then at 2:30, Morgan will be joining Julia. Okay. Other questions about that? All right, and then the exam, same place, same time. You're just going to arrive sometime between 6:15 and 7:30. So that leaves you at least an hour and a half, which should be enough time for the exam. It's 26 questions, okay? 26 questions. Similar format to the last one, but the material, of course, is what we covered since the last one, according to the review outline. Any other announcements that I need to make? Review sessions, the exam itself. Oh, so I sent the email out for if you absolutely can't make that time tomorrow night. If you have not replied to that email, do so this afternoon. So what always happens is I say that, and then I give you a little more time, and then I send the email out to everyone who responded, and then there's still more people that respond to the original email. So if you have a conflict Wednesday night, respond this afternoon. Respond this, not tomorrow morning, this afternoon. Okay, it's an organizational difficulty for me if you don't just everyone respond this afternoon. If you can't make the test tomorrow night, it makes it a lot easier. Okay. Other questions? Yes, sir.
Do we need a calculator?
You may have a calculator for this one. Do you need it? I don't know if you need it. Maybe one question or something. I don't even think you need it, but you can bring one. Other questions? Okay, so we've been on this journey, and so let's do some summary review of the big picture, which is arguably the most important thing to always have in mind when you're doing all these problems, homework problems, quiz problems. How do they fit into the big picture of what we're doing? There should be coherence with everything that we're teaching, and everything you're learning should coherently fit into into a whole. All right, so at the beginning we said that calculus is about 2 things. You know how much of a quantity you have at every moment. You want to know how fast it's changing at every moment. And then the reverse. You know how fast a quantity is changing at every moment. You want to know how much of it you have at every moment. So, have we been working on goal A or goal B? We all ought to know the answer to that. We've been working in goal B. You know how fast a quantity is changing every moment, and you want to know how much you have at every moment. Goal A is the matter of differential calculus, And goal B is the matter of integral calculus. That's where we talked about integral. We introduced integral last time. So we are talking about integral calculus. And so let's bring it back and kind of show the big picture related to the sand, unloading sand example. You know how fast the quantity is changing every moment. What is that? What kind of rate of change? Exact rate of change function. So that's our exact rate of change function. We have this sand unloading exact rate function, right? It comes out slow at first, and then most of it comes out in the middle at a high rate, and then towards the end, it's still coming out, but at a slow rate again, right? And you can imagine that as a truck unloading sand onto a scale. Okay, you can imagine that's how the rate would go. Okay, and so our goal is, you know how much of it you have at every moment. And what's that? This is the final goal. What is how much of it you have at every moment? Exact accumulation, whether that's net accumulation or total accumulation, which are just very similar, right? So we want exact accumulation. And here I'm showing the exact net accumulation, which is what? Amount of change, right? It's giving the exact amount of change since our starting point, x equals a. Okay, so what was our process over the last 3 weeks? We've made a process to get from this point to this point. So where did we start? We had the exact rate of change function, and what did we do? We took that and we built an approximate rate function, right? So how do we get from there to there? We start with an approximate rate function, and that consisted of constant rates of change that we took from the actual rate. So we build a new function of constant rates that's trying to be like the exact rate function, right? It's trying to be like that exact rate function. But the key to it is that it's built on constant rates. And why do we want that? Why do we want constant rates? I mean, we just made the function worse, right? We had the exact, and we just made it different and worse. So why do we want the constant rates? Yeah. Right. How do we do so? It's through constant rates that we can generate values of changes, exact accumulation. How can we do it? What's the key? It's what we worked on all semester long, right? But how do we go from a constant rate to amount of change? M dx. dy equals m dx. That's why we spent 3 weeks at the beginning of the course on that, because this is the key to getting from exact rate to exact accumulation. M dx, if we have a constant rate. So the constant rate function was that we used the left function with the exact function, but then what do we do? R dx, right? So you see it right there. A constant rate, we can get a little change in accumulation by this, right? And that's m dx, right? It's just the m is what represented as function notation because it's coming from the r function, right? So we're using outputs or values of the dependent value of r to be our m's, right? So then we're gonna, once we get lots of those changes, we're gonna sum them up, right? And we sum them up. We're summing up to get a total net accumulation, or all the little changes makes up the whole net accumulation, right? We sum those up. And that's the basis. That was the whole basis of that approximate accumulation function, right? Summing up m dx's. That's the bottom line of that thing. Okay. And then, how did we get then from the approximate accumulation function to exact accumulation? What was the key to that? So we've got this good approximate, or maybe not so good in either case. How do we get then to this elusive exact accumulation function?
Increase the size of delta.
Right, so these delta x's are very unrealistic, right? They're huge moments, and we said a moment should be small, right? We said a moment should be small. When a moment is small, then we can really assume constant rate of change. So we want, if we have realistic small moments, then our approximate accumulation function A, we can consider it to be exact. So we just make the changes small enough. Once those get small enough, we can't distinguish between exact and approximate. And that leads us back to the exact, okay? So that was that process we've been working on for the last 2 or 3 weeks. But now that we've done that, okay, so now we've kind of earned the right to just go directly from exact rate to exact accumulation, because we made that journey and we did all the heavy lifting of that. And so now that we've earned the right to just go from exact rate of change to exact accumulation, and how do we do that? This is integral, right? This is integral. Okay, so integral. So you notice in the integral equation, what do you see? You see this, which is what? What's this?
MDX.
Nope, just look at what I'm underlining. But it's exact rate, right? It's exact rate. And yes, that's MDX right there. So again, we're summing up a bunch of MDXs, so it's the same principle. But now this is the exact rate of change function. And from it, we get the exact accumulation function. So the integral function is like it bypasses all that stuff that we worked on, that we had to work on to understand what this is talking about. Because when we see this, you should be thinking that long A equation with a really small delta x, right? When you see that, that's what should come to mind. Oh, it's that long thing that we worked for 2 weeks on for a really small delta x. Okay? But having done that, now we've kind of earned the right to use this and go straight from exact rate, right there, to writing down what the exact accumulation is. Knowing it's the long A equation, right? It's the long A equation for a small delta x. Okay, so this is a slide we looked at last time, so it's good to review. So remember, that's our long A equation, the approximate net accumulation function. And so then our exact net accumulation function is what we just said, right? These are almost one and the same, right? These are almost one and the same. The only difference is the second one is the first one when? When what? Delta x is really small. Okay? And we're gonna break down how they are the same in a second here. So we're gonna have a really good slide where you guys get to talk and see how these two things are very much one and the same. We'll break it down piece by piece. Okay? So what is this? It's A sub f of x is the accumulation of changes in f due to its changing at a rate of r sub f at every moment t from a to x. Okay? At every moment t from a to x. So this kind of hints at the reason why we need, we'll talk about it later in class, but why do we need, because this t is essentially what variable? It's essentially x, so why don't we just put x there? Why do we need that separate x and then this new version of x that we call t? All right, so this hints at it, and we'll talk about it later. But
Because t is x values between a and x is the actual endpoint.
right, and so yes, exactly. And the question is, why do we have to have that? Yeah. So yeah, you're exactly right. Yeah, and that's what this is saying, right? So changing at a rate at every moment t from a to x, right? That's the thing. Okay, so now what about, did we get this far last time? I don't remember. Did we talk about exact total accumulation? Or did we just stop at the exact net? So what's exact total accumulation? That means that doesn't track changes, that tracks all of the accumulation, right? So there could have been some accumulation already when we started. So whereas the one before tracks the change from when we started, this one keeps track of all the accumulation. So for instance, if there were p hundredth pounds of sand on the scale, then the function f would be the total accumulation of weight in x seconds. So how would that be different than the a sub f function? How would we write the function f? The function f would be what? Yeah.
It would be p plus then the exact net accumulation.
Well said, right. So we have the same amount of change, but we'd start off with this amount. So then the function f, which would be the total accumulation, would be p plus how much it changes since a, right? So p is how much accumulated up to a, and then we got the amount of change from a to x, and that gives us the total accumulation. Okay, so it's kind of like a fifth function in our progression, right? First in this progression of, you know how fast a function is, or you know how fast a quantity is changing at every moment. You want to know how much you have at every moment. It's kind of like a fifth thing, right? So we go from exact rate of change to approximate rate of change to approximate accumulation, net accumulation, to exact net accumulation, and then if there was some stuff there, whatever the quantity is, at A, then we can write an exact total accumulation as the amount of stuff we had plus now the additional net change. Yes, sir?
So is it safe to say that P would equal Y initial?
Okay, so what do you think? Y initial. So that actually was my next question. Is P a value of X or of Y?
Y.
P is a value of the quantity, right? So here's he's proposing. He's proposing that P is Y initial. And then what would that be? Does it work? Does that work? Yeah, and so we're seeing it again, right? So that's really good observation that we could think of this, the total accumulation function, as initial value plus the change. Y initial plus the change in Y. So still another place where that's showing up. So yeah, really good. Okay. All right, so let's skip this. We don't need to do that one. So now let's talk about, here's our exact net accumulation, right? And what did we say? We said think of this as this. How? How do we think of the first one as the second one? Right, with a small enough delta x so that, so here we're going to take that idea a step further, with a small enough value of delta x so that values of A are indistinguishable from the exact accumulation. And then what would that be in terms of the completed intervals versus the partial interval, right? What is that? It's the partial interval, the delta x's are so small that the partial interval is really adding no contribution anymore. Because they're all so super small, right? So it's kind of like when delta x gets small enough, we don't have to worry about the partial interval anymore. See that? Let's do it again. Here we go. Ready? All right. Gone, right? So when delta x is really small, it's like the partial interval, what we get from the partial interval is just negligible. It's just not, we can just ignore it. Okay? So now we've got delta x is really small. How are these two things the same? So how are they the same? So, okay, so we're going to go through this 1 through 6. And you're going to talk about this. We know how fast something is changing. So every item shows up in both of these expressions. Every item. So we know how fast something is changing. You're going to talk, and you're going to talk to the person next to you, and you're going to say, where we know how fast something is changing is showing up in each of those. We know how much, we want to know how much of it we have. Where does that show up in each of those? Which is found by summing up. Again, where is it shown in each? Summing up many bits of change from the starting value of x to the current value of x. So just go up to number 6. And for each one of those things, 1 through 6, how are they both expressed? How is it expressed in both expressions? Okay? Talk. Lots of talking here. Go. You know how fast something is changing. Where do we see that in the top one? The rate function, the exact rate. Where do we see in the bottom one? Right, so it's that. And the function notation for R in the bottom one, you got to see is, you have to see it's this whole thing, right? That is a value, try that again. That whole thing is the value of R. So don't let that what we're putting into R as the independent, as that expression, that's just the x value, right? The what? The left side of every completed interval. You got to see that whole thing that I've highlighted as using function notation for R to get a value of R. And then we're going to take that value of R and do what? Multiply it by delta x here. So there it is. M dx, right? M times change in x. Okay, so yeah, we got a rate function. We want to know how much of it we have. So I just gave it away. Let's see. So that is either the accumulation, right? The amount of accumulation. That's how much of it we have. So if you put the whole right side and both of them, that would be right too. Right? The whole expression on the right for both of them is how much we have. Add x, right? Add x. Okay, next one, which is found by summing up. Where do we see that in the first one? Integral is German for sum, S, right? That's a German S for sum. What about the second one? Greek sigma. Okay, Greek sigma. So we're both summing up bits of change. Where do we see the bit of change in the first one? Which is our what?
The rate times the small change.
Right. That's our delta y or dy. Delta y or dy, right? And then in the second one, same thing. Rate times change in x. Which I said before. What we worked on in we've been working out the whole semester, but just exclusively in the first 3 weeks, right? Rate times change in x gives change in y. And we're summing a bunch of those up. Starting value of x. What's our starting value of x? A, right? A. The current value of x. X, right? X. So any particular value of these functions is the net accumulation starting from A up until x. And then it's a function. That x varies, right? So that x varies, and we get all the amounts of net accumulation for any x. Okay, independent variable of each function is what? What is the independent variable? Variables are letters. What letter is the independent variable? X for both of them, right? X is the independent variable. What does it mean? So in terms of the net amount of accumulation that we have, what is X? Yeah. Oh.
Value of x in the interval one x or would it be t? And this only works between a.
Okay, so that all right. So this goes. Let's answer my question. I think maybe it'll help. So the question I asked is, what is the meaning of X in these functions, according to accumulation, net accumulation?
It's the time that we're accumulating up to.
Okay, yeah. So it might be time. It doesn't necessarily have to be a time variable, but the end. What you said at the end was right. So X is where we accumulate up to. It's the right hand side of the whole interval of x for which we're finding the net accumulation. It's always the final value, but then that final value increases. It's because it's a function. Okay? So we talked about all the completed intervals and then the partial interval, where the current value of x, our independent variable, is in that. It's at the far right side within that current interval. So if we ever pause the situation, x is the far right hand x value of all this stuff that we're adding up. Does that answer it now?
Yes. If that first calculation you say a of f of t equals that exact expression, would that still be valid?
No. So we're gonna talk. So t, like we said before, t takes on this for any given value, current value of x. T has to take on all the x values between a and x. Remember, it's going to move through completed intervals and the current interval to get all that amount of accumulation. So yeah, AF of t won't work. That won't work. Okay, dependent variable for each is net accumulation or net change, right? Net change. And when delta x is small enough, they're both exact, right? They're both exact, and that's what we're talking about, right? We're seeing that second one as delta x being small enough, so they're both giving us exact net accumulation. Okay, and any questions on this very important slide? Why is it so important? Because the reason, again, why it's so important is in calculus you come to integrals all the time. You're going to be writing them down. They'll be given to you in problems. So what is your image? What are you thinking about when you see integral? You should be thinking this. You should be thinking this. All that we learned about that. That it's summing up little bits of change starting at A all the way until the current value of x. Okay? So super important slide. What are we going to do next? Okay, so let's put it to work. Let's put it to work. Here's an example. If you just want to jot down enough to make progress on this, and then you can come back if you want to take a screenshot of it from the video. But here's an example that's going to test some of our understanding here. A tub has a clogged drain that lets some of its water through. At t equals 0 minutes, the faucet is turned on. The following graph shows the rate of change of volume of water in the tub in gallons per minute as a function of the time in minutes. Okay, so the drain is clogged. It's letting some water through though. And then at t equals 0, we turn the faucet on. And so now this is the rate of change of the amount of water in the tub when that's all that's happening, okay? So questions A through E, see if we can do this in about 7 or 8 minutes. Okay. So we need an expression for A sub V So now our independent variable is t. All right, so we want a sub v of t. No, down here. A sub v of t. How are we going to write? So this is what? Exact net accumulation. Exact net accumulation. How do we write that? Right, so we did all this work so that we could legitimately write integral. The integral from a to, so you could put anything else you want here except t. Doesn't have to be x, so it could be, if you put x, that's fine. I'm going to put u. Okay? So the integral from a to u of RV of u, no, sorry, t. No, t, you guys, sorry, my fault. The independent variable is what? It's where we're accumulating to on the right side. So it needs to be integral from a to, the t needs to be here, right? Because that independent variable, like we talked about before, what? It's the final value of the current amount of accumulation, right? For x, right? Or for the horizontal variable, right? So it's that right-hand side of the far right side. So if it's our independent variable here, it needs to be at the top of the integral sign. Because we're a, so a to t, a to t. The far right side of everything, right? So then now we need to pick something else. So here's where I'll pick u, right? So I'll pick u. And what does u represent? It represents all t values from a to t, right? So it still is a t value, but it's representing the t's changing from a all the way up to t. Okay, but so we know the rule of that though, right? So we could also write this way. We could put the rule in there, and then you'll see this often, right? You see this often? 0.03 u squared minus 0.6 u plus 2. Sweet. Ha, power. All right. What? du. 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 Okay? So we know what that function r sub v of u is, or you could have put r sub v of x, right? You might have put r sub v of x dx. All right? Really bad 0.6. Okay, there we go. Better. So the point is that you can use function notation to represent a dependent variable of the rate function, or you can use the rule. You can put the rule in there because they're the same, right? They're representing the same thing. Represent the dependent variable. So does that make sense? That you can do that, and you'll see it both ways. You'll see them written this way with just function notation, and then oftentimes you'll be given integrals and problems where you'll have the rule there, and that's just what. So what is this? You'll recognize that as what kind of function? Rate of change, right? Rate of change. When you're given an integral and you see a rule like that, du or dx or dt, then that function is a rate of change function. That's a rate of change, a rule for a rate of change function. Does d make sense? Okay, so then what would the function v be? V of t. What's that? Yeah.
I have a question for you. Don't you have to add plus 2.5
Okay, do we add the 2.5 and part D?
No.
Because what is it asking for? We want the accumulated changes in volume, t minutes. So it's asking for the accumulated changes in volume. So is that net accumulation or total accumulation? Does that make sense? Yeah. So because it's specifying accumulated changes, it's saying the net from time equals 0, or how much change we had from time equals 0. That's just our integral. Now what about E? Total volume is?
2.5 plus the
Right, so our y initial, or our accumulated up to time equals 0. So this is the amount of, what is that? That's the amount of gallons in the tub when we turn the water on, right? Plus the amount of change up to t. I'll stick with you. If you had x, that's fine. If you have anything, any other symbol, it's going to be fine. Something different. R sub v of c, dc, whatever. R sub v of x, dx. Just something that's going to signify all t values from a to t. Yes, sir?
would it be okay to put 0 in place of a, since that's where we're starting?
Yeah, absolutely. Good point. What is the starting value of t? We know what it is. A equals 0. He's right. So we can come here, and this is better because we know what a is in this situation. 0. And same thing down here. Very good. We know what a is, so we can write down what its value is. It's 0. Here too.
U is r sub v of t. Actual number would be
Okay, so what does this represent? So when you see this, you think about you think about that A equation, right? For a very small delta x. And what does that A equation do for a very small delta x? It sums up all the accumulation due to completed intervals. How many?
X minus
A lot, right? If delta x is really small, there's going to be a lot of completed intervals. So in terms of, you said computing or calculating this. We don't really do that. This represents this process of summing up a gazillion amounts of change. So, and this is a good, so this is a new kind of function that's different than the ones you're used to in the past, right? Functions you're used to in the past are like this. Y equals x squared plus 3x. F of x equals sine x. G of a equals square root of a times e to the a, right? So what's the point? So these give rapid fire results, right? You You can plug in values of the independent, and it just cranks out values of the dependent really fast, right? This isn't like that. This is reflecting process. It's reflecting this process of this really, really long sum. So it doesn't have this quality of rapid fire results the way functions you're used to do, right? Okay, so this is called, all the functions you've dealt with in the past in your math career. This is important. We're given in closed form. Closed form. That's a C. This integral function, I was about to show a slide on this, okay? So I'm not diverting, okay? I was just about to show a slide about this, all right? So an integral function is an example, and for many of you, the first example you've ever seen of what's called open form. Why? It's representing a process that doesn't yield easy computable results. We need technology, right? We need technology to do some kind of numerical method of adding up a whole bunch of little changes to give us a value of that. Okay? So the difference between what you're used to in the past, closed form expressions, and open form. This is going to be language we use. Okay? And like I said,
get lots of questions about what the difference in these two forms are. So make sure that you pay attention and ask questions if
Yeah.
you don't see the difference in these two forms.
okay, one more time. Closed form, rapid fire results. When A is 3, G of 3, we can get it, right? When A is 10, G of 10. We just crank out values of dependent variable. That's closed form. Open form is reflecting a process, and we can't really do that. We can't just quickly do something in our calculator to get a value. We need like technology like GC to work out that process for us and give us a value. So that's open form. Reflects a process. Okay. Other questions on, and then again, I could have come in here and written the rule for R sub V of U. I could have written the rule for R sub V of U just like I did over here. So those are interchangeable, right? Interchangeable. Sometimes you'll see the rule. Sometimes you'll just see the function represented with the function notation. What's that?
Is that what makes an open equation? One of your variables is infinite?
Kinda. So, no, it's anything that's not readily computable and reflects some process, some mathematical process, rather than like a formula that just gives you results, just like that.
The independent variable in the one up top is A. The independent variable in the one at the bottom is B. So you have an independent variable of both of those functions. It's not, look at the right-hand side of the equation is the function rule. That's the difference that you should notice. So notice that with G of A up top, we already have a function rule where no matter what A value I have, I can plug it in really fast and I can automatically tell you how much stuff I have. Whereas at the bottom, because I have an integral sign in there, the whole integral is not an easy thing that I can just quickly plug into and get back an output very quickly.
Is it better?
So any summation, integration, any of those functions are now open?
Just for now, just know that this is an open form because it reflects a process. But you're not going to be quizzed on, here's a bunch of things, are they open or closed? Don't worry about that. Just know that an integral is maybe your first experience of an open form expression. And then we're good there, yeah.
So a closed form would represent some kind of formula which you could work through and get a definite result, while open form represents a process that's more general. So,
Yeah.
so for example, a squared plus b squared equals c squared, Pythagorean theorem, is not a general thing. You figure out each of those values, but say for this integral here, some of these values are thinking about it in terms of general. So rather than you finding a specific value, like, you plug in one thing and almost immediately it gives you something else, you have to work, unless you have GC.
So what is v of 1? V of 1 would be 2.5 plus 0 to 1 of r sub v u du. What's the value of that? What's the value of that I put a cloud around? Could you give me the meaning of it? You should be able to give me the meaning of it. That is a value, first of all. It does equal some number. There is some number that equals that for this problem. What would that number mean? What would that number mean? No, what I put the cloud around. Yeah, just how would you explain it to a 5-year-old who's taking a bath? What that number is. How would you explain it to a 5-year-old who you're giving a bath to? What that number is? Tell the person next to you. Tell the person next to you. Okay, let's hear from you. So, what do you think? How would you explain to a 5-year-old what that number represents? Was that a hand? No. Yeah. How much? What did you say? How much total water is in the bathtub? Is the total amount of water in the bathtub? What I put a cloud around?
No.
No, not quite. Yeah.
It's just the amount of water you add to the bathtub.
Okay. Is it the amount of water that we added to the bathtub? Okay. Which amount of water?
1 minute of water.
The first minute from time equals 0 to 1. Yeah. So from starting at time equals 0, it's how much water we added in the first minute. It's how much water got added in the first minute. Okay. How much is it? Right? We don't know. So it represents that perfectly well, but I can't come over here and say, oh, it's 1 squared plus 3 times 1 equals 4 gallons. You see? See the difference? In that first formula up there, I plug in 1, I get 4. Here, I plug in 1, I know what it means, but I can't by hand or quickly with a calculator get that. So we need technology. Did you?
Yeah, I did just.
So he put the integral into GC, and then you put a 0 to 1, and what'd you get?
I got V of 1 is 2.5 somehow. Don't ask me.
No, something's wrong.
I know.
It's gonna be more than 2.5. Okay. So yeah, so let's do it. Here we go. All right, I'm gonna erase. So I'm sure someone jotted down the function, right? Let's take a look. Here we go. Okay, what was the function? R sub v.
R sub v of t over
0.03 u squared
Okay.
minus 0.6 u plus 2.
All right, and so then, so A okay, how should I write this function?
2.5 plus.
Is it 2.5 plus? Look at what I wrote. All right, it's going to be from 0 to t of. So I could type in the rule again here, but I've already defined that function as r sub v. So to make it easy on myself here, I'm going to Is that what we said a sub v of t was? Do I have that written in there right? And based on the r sub v function.
But you didn't. But in the top one you use t's, and there you use.
Okay, so do I need to change it? So in the top one, I'm defining a function. It doesn't matter what I put in. It's just a dummy variable. I could have put A's in there. I could have put X's. It's just defining the relationship, regardless of what symbol I chose. So that's why we call that symbol a dummy variable in defining a function. I could have made it a C everywhere. I could have made it D's everywhere. X's everywhere. It doesn't matter. It just defines that relationship of that rate function. Okay? And so then down here, same thing. I could have... This is also kind of like a dummy variable. I could choose any symbol for that. But I have to match these, right? If I want that integral function to be integrating or accumulating up to t as my independent variable, those have to match, okay? So now, what did I say? We're going to look at a sub v of 1, right? So here's the thing with an open form expression. I need technology to do it for me. I can get a number, but technology has to do it for me. I can't just do it by hand or quickly with a calculator. So what is it doing? It's doing a summation much like the long A equation. That's what GC is doing. It's using some kind of summation algorithm like the long form A equation to get that.
1.71.
1.71. So in the first second, 1.71 gallons. First minute, 1.71 gallons were added to the tub. And so what's V of 1 then? So V of 1 would be 2.5 plus that, right? That would be the total amount of,
4.21.
yeah, 4.21. Okay, questions? So, really important. I'm not wasting time by digressing. This was a really important digression, that you understand how these functions work. Ask if you have a question. Are you good? What?
If you were to graph out coordinate system, you would use that.
I can't hear you.
If you were to graph this out on a coordinate,
What's this?
that
Yeah.
equation,
I got two equations up there. Which one?
the first,
The first one is the graph I gave you.
could you use geometry to calculate the accumulation?
Yeah, but that would take our focus off of the quantities of volume and rate of change of volume. We want to stay focused on that. So you want to use volume and area or something like this. What does that have to do with gallons and rate of change of gallons? So we want to stay focused there on those things. Yeah.
I just want something on, I graphed both the A of x and, no, A of V of x and V of x, and while they look generally similar, in certain parts it's as if the endpoints are coming together.
Okay, why don't you, based on the rate of change function, I want you to make a sketch of what you think A sub v of t would be and what v of t would be. So based on the visual of the rate function that I gave you, hopefully you sketched it, or I'll put it back up there. Sketch what you think A sub v of t would be and what v of t would be. So I'll put it back up. Here we go. There it is. That's R sub v of t. So based on that, sketch what you think A sub v of t would look like and what v of t would look like. A sub v of t is going to start where? Right, because it's going to track changes. The changes from your starting point will always start at 0, right? The amount of change. And what's it going to do? It's going to increase, okay, until when?
Until just after 4, then it's going to level off and be flat and then start coming back down.
Okay, so he wants increasing up till about 4.2 minutes and then be level and then start coming back down after that. Agree? So maybe something like this. What do you think? What will V of t look like? Okay, let's let GC do it and see how we do. So I want to graph y equals, right? If I want to graph, I do y equals a sub v of, I want to graph it now. So I need to do x. And before, I'm going to turn it off before I do that. And then I want to graph v. So how do I define v? V of, sure, we could use x as a dummy variable, that's fine, equals 2.5 plus, yeah, so use function notation, right? I could do that, I could write the integral again, or I could just write a sub v of x. Okay, is that going to graph it? Nope, that's just to find it, right? That's just to find it. Now I need y equals v of x. Okay, what do we say? So let's look at a sub v. Let's see if it's right. How do we do? Was it 0 to 7?
Yes.
And then you thought this would look like that. Shoot. Shift it up. Okay, so these integral functions, they're open form, so we need technology to either calculate values or show us plots at this point. Okay, what do we need to do here? We got 5 minutes, 4 minutes. So we'll hold off on this. I do want to talk about one more thing, but this is good. It's more practice, so kind of the same stuff. It says quiz, but it's not. It's just more practice for the exam tomorrow night. Similar to what we just did. But I want to do one more thing. Just want to practice starting now and through your whole calculus career, you'll be coming to integrals all the time. So again, what is your image? What does it mean? And so we look at this right here, and we could say, what? That is an amount, it's a net accumulation starting at what? 4. And what else do we know? That amount is accumulating at a rate of g of t, or g of x, whatever, okay? So yeah, so this is the net accumulation starting at 4 to x, where the accumulation is occurring at a rate of change of g. What about this one? Right, so danger, right? Danger, this is not going to be what we intend it to be. Okay? Because those x's match. Let me just quickly give you an explanation of that. So if the rate of change function was like this, say this is r sub h of x. It's going from -3, so I'll just do like that. So here's -3. And say here is x. What does r sub h of x mean? R sub h of x would be this rate at x. And so if I integrate, or if I accumulate starting at 3, this is saying I'm going to accumulate what? At this constant rate that is the rate at this rate. So it's not going to accumulate changes at the changing rate, but instead, if I use an x and an x, it's going to accumulate the whole time at the rate at x. This is r sub h of x, if this is our x value. So what's that going to, is the result going to be too big or too small? too big because it's going to accumulate at that constant rate, which is the rate at the end, the whole way from -3 to that x, rather than along according to the changing rate function. So to make it according to the changing rate function, we need to come in here and change it to another variable like we've been doing. Say t. Now t can change from -3 to x. And as it does that, we'll get all the different values of the rate as we're summing up those little bits of change. So then that would work. Okay, one more thing. So that expression that's no longer a function, right? That's just a value. That's a number. Because it's like we're starting accumulating at 10, but we know exactly where we're going to end. And we have this change. We have the rate function, but so we're going to accumulate starting at 10 and ending at 15. That is a number. So if you put that in GC, it's going to give you a number. And what is that number? The amount of accumulation as x changes from 10 to 15. If the rate is a sine e to the a. So an expression like that is a number, or like a particular value of a function, right? So it's like we're plugging in 15 to some function 10 to the x, a sine e to the a dA. When we plug it in, we get a particular value of net accumulation. Okay, so that blue sheet will serve as good review for the exam, plus all the materials online. See you tomorrow night. Yeah.
On this one you just did,
Yeah.
would that be basically doing the same thing as doing 10 by x and writing x?
So the value, yes, exactly. So it's like a function. That's kind of what I said there.
Define as x equals 15, and then give me the
Right, so it's some function 10 to x, a sine e to the a, and we could call it just a g of x. So what is it when x is 15? That's the value of g of 15.
g of 15. Okay,
This is the particular value of the dependent variable when x is 15.
yeah. Thanks.